Hello, everybody. How are you? Nice to meet you. And it's Saturday night, live from Pittsburgh, Pennsylvania. And we're happy to welcome you back to another session where we're going to talk about some interesting mathematics. And we're also going to discuss whether or not, whether or not there are some other interesting directions that you can look at math with. What do I mean by this? Well, we actually have a wonderful collaboration today, and we're happy to be working with the Los Angeles Math Circle. Now, Los Angeles is a place that I can actually relate to quite well. I lived in Los Angeles for 6 years. And in fact, this is the Los Angeles Math Circle, which is organized by UCLA. And UCLA is where I spent 2 years. In fact, I used to live on the intersection of Kelton and Levering Avenue, if any of you are familiar with the UCLA area. Now, whenever there's a math circle, that means that there are some interesting problems. And what we're doing for today's collaboration is that the UCLA Math Circle attendees had made some questions that they were interested in asking. And so what we're going to do is we're going to talk through some of those questions. I myself haven't really looked at those questions yet, because that keeps the live part of this talk. If you have not been here before, I want to welcome you to an impromptu improvisational show where what you'll see is how we think about questions, and then we'll see how we respond to questions that people might have about all kinds of different questions about maybe how you study math or what math is about and so on. And the way we'll organize our time is that at the beginning, we're going to work on these questions that Los Angeles Math Circle gave us, and then we'll open up for questions at the end. Everyone ready? So I'm going to go and switch to the questions they've got here. And I also want to say, it looks to me like our contrast, our brightness on today's video is a bit too dim. So I'm going to adjust the camera to make it a little bit more bright, and then we'll continue. Just a second. Meanwhile, I'm going to go ahead and put their pieces on. 1 second. Right, because you can at least see their logo and the info about them while I'm adjusting the brightness of the camera. 1 moment, please. Much better. So actually, the way this camera works is that it's quite sensitive, and so usually when we're when we're doing these live streams during the day, which we do every day, we have a different setting for how bright this is. But apparently it's getting dark already. So, let's see. Well, what kind of questions do we have to talk about today? Oh, and maybe a few things to say about Los Angeles Math Circle. This is actually an organization that I spoke to while I was a graduate student, back when I also spent some time at UCLA. So I had the opportunity to speak to their students back then and there. And I guess it's nice to do it again here remotely. And it looks like they have over 300 elementary, middle, and high school students during the academic year, and over 100 new students each summer. All right. Let's go ahead. Yes, I already see that somebody on the live stream is asking about Terence Tao. It was very interesting to be at UCLA. I even took a class from Terence Tao, and he is really a very interesting person in person. Great. What kind of questions do we have? From a 7th grader who attends the UCLA Math Circle. This person would like to know about non-polynomial time hard, NP hard problems. Oh, this is interesting. Okay. So you're saying you want to learn about NP hard problems, where NP stands for non-polynomial time. Obviously, that's what the N stands for, because it's an N for non, right? That's what I thought too for a really long time. Anyway, I'll explain this. So I've heard about how they must be able to be solved in polynomial time to not count as non-polynomial time hard, but the field seems mysterious to me. Can you explain NP hard problems with examples and best solutions so far to them? Oh my. Okay. Well, you see, there's this famous problem in math. And in fact, it's so famous that you can get $1 million prize for it. $1 million US. I want to write prize. Okay? There's a $1 million prize for this problem. And this problem is to decide whether or not P, it's called P versus NP. But really what they're asking is P equal to NP? Well, you know, what do these mean? Okay, so P means that P is like a class of problems. It's like a bunch of problems that you can solve in a polynomial amount of time. What that means is that somehow if you have 100 pieces of input, how many calculations do you need to do to figure out the answer? It should be a polynomial of 100. So that, for example, if you have to do it for 1,000 pieces of input, you only have to do, you know, a polynomial where you plug in 1,000. Whereas there are some things which are unfortunately exponential time. There are some things for which if you have n inputs, it takes 2 to the power n operations. And if you tried putting in 100 as n or 1,000 as n, unfortunately 2 to the 100 and 2 to the 1,000 are just like totally different. 2 to the 1,000 is enormously more. So that's why people are curious about the polynomial time set of problems. Polynomial time, P14, Y3, R0, N3 says that you're lost. Well, let's put it this way. If somebody gave you a job to do, and the job was something where if you have to do something where you have like maybe you have to sort some things in order, you know? I've got to sort 10 things in order. How many operations, how many moves do I need to do to sort 10 things in order? The good news is that it actually doesn't take that long. Some of you know how to sort 10 things in order. All you do is you just kind of, there's something called even insertion sort, where you kind of, you make a little pile of them that are in order so far, then you get another one that you want to put into order. Imagine that they're all like homeworks or something, and you just go put it in the right place. And what you could imagine is this doesn't take you too long. You could do it. If you had 10 things, you do it, and it won't take you insanely long. If you had 100 things, how much longer would it take? Maybe a bit more than 10 times as long, but not crazy. But now, if you have a different kind of a job, imagine that the job was something like, well, what's a good example of a job? Yeah, imagine that the job was something else. Imagine that the job was that you were supposed to list all of the different ways to rearrange 10 people. Suppose that was your job. Write a list. And the list is supposed to be, you could put them as 1, 2, 3, 4, 5, 6 up to 10. Here's another one. 1, 3, 2, 4, 5, 6, 7, 8 up to 10. Or, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Would anyone here want to write a list of all of the different ways to arrange the numbers from 1 to 10? Is there anyone here who wants to do that? Actually, that's no fun. And that takes a long time, right? That takes a long time. That's like 10 factorial different or rearrangements. But if that's how hard it is for 10, how about 100? Is 100 just 10 times as bad? Like if you had the patience to go and list all of the different ways to order the numbers from 1 to 10, and someone said, I challenge you to do 100, would you say, it's just 10 times as hard, no big deal? Oh, it's awful. If you wanted to try to write down all the rearrangements of the numbers from 1 to 100, it's not just 100 times as bad as doing 10, like the rearrangements of 10. It's like 10 factorial versus 100 factorial. I see that Shanti Liu says, just ask a computer. If you ask a computer to list all the different ways to arrange the numbers from 1 to the 100, the computer will not be able to do it. It's actually, yes, the computer would rage quit before they finished 1%. Even the computer would rage quit in a big puff of smoke as it overheated and it couldn't handle it anymore. It's because 100 factorial is enormous, right? So I'm just explaining that. That's why people care about efficient things. Efficient things are somehow where if you had 10 things to do or 100 things to do, you can say how much work is it? And P means the amount of work is some polynomial. Polynomial can be like take n to the power 3. And maybe it's n cubed as much work. That's no big deal. But 2 to the power n is crazy. Okay, what is NP? Well, here's what I thought for the longest part of my life. I used to think that NP meant not polynomial time, right? It's like n stands for not, right? So it's like you got some things which are P, polynomial time. It takes a polynomial in the number of the size of the input, many operations to do. And n just means not polynomial time. That's what I thought. But then I didn't understand how you could get $1 million for proving this. For deciding this. Because, if P stands for the stuff that's polynomial time, and NP stands for the stuff that's not polynomial time, then I guess, obviously they're different, right? Well, unfortunately, that's not what n means. N doesn't mean not polynomial, right? So the n is actually not the non. So that's the thing that I want to change about this. Actually, what the n means is it means that it's called non-deterministically polynomial. Okay, now my head is too big. I'll write it under here. This n stands for non-deterministically. Oh my goodness. Okay, what does that mean? I also see that some people are saying that there's some audio unevenness about the audio here. I don't exactly know why. I wonder if it's something on the YouTube side, and I apologize for that. But what could non-deterministically polynomial time mean? So, non-deterministically, does anyone know what... yes, Shanxi Lu asked, has anyone got the prize money? Actually, no, nobody has figured this out yet. This is one of the biggest problems in the world right now. So, does anyone know what non-deterministically means, just as a word? This is a definition. It's an English word. Do you know what that means? Yes, spaced out says, I don't know, it can't be determined, right? Non-deterministic generally means random, more or less, okay? So when somebody says non-deterministically something, it means you can't guarantee it. Deterministically means guaranteed. Let me give you an example of something that's non-deterministic, non-deterministically efficient, right? Suppose what was going on is that you were hunting for your shoes. I don't know how you lose your shoes, but I'm imagining that you somehow have your shoes, and you lost your shoes somewhere in the streets of Manhattan. It's really unfortunate. There's some shoes that you lost in the streets of Manhattan. And now you're going to go and hunt for these shoes. I'm not exactly sure you hunt for the shoes without wearing shoes, but please bear with my analogy for now. So, you see, suppose that as you're hunting for these shoes, you just so happen to walk just into the right place, and you're like, there are my shoes. You would say, I got lucky, right? So somehow it's like as you're hunting for something, it is possible that you could get lucky and just happen to walk in the right place and be like, there are the shoes, right? Got lucky. And in fact, luck, randomness, this is all related. But the reason why you'd say you got lucky is because there's also, I see, somebody said good luck with that earlier too. But the reason why this is so interesting is because there's also many ways to find your shoes the long way, where you kind of just like walk around and around and around and around, and finally you find the shoes. So non-deterministically, when something is non-deterministically efficient, what it means is that, the P stands for efficient by the way, it means that somehow you could get lucky. And if you got lucky, you'd be able to verify that you were right in polynomial time. That's what this means. Non-deterministically polynomial time means I have a problem. And if you just got lucky, you could check. You could verify that you were actually right, that you got the answer in only polynomial time. Now we got some examples. So the first example here is given a connected graph. Can its vertices be colored with two colors? Oh, this is actually polynomial time. So I want to change this word 2 into 3. Okay? 3. We're going to change it to 3. When you change it to 3, it becomes quite hard. So now the question is, can the vertices be colored using 3 colors so that no edge is monochromatic? What does that mean? Let me try to draw a picture. Okay, we're going to use 3. And actually what we're going to do is, because there are a few questions people asked, I'm going to go a bit fast. I'm not going to answer all of this one, because I want to get to the other questions that were asked too. So over here, fluctuating volume. I really wish I knew what was going on there. Okay. Well, you know what? Since you are asking, I'm going to go and right-click on my volume setting here and see if there's anything funny with it. I'm going to flip it. Okay, that's there. And I want to see if any filters are applied. No filters are applied. All right. I don't have a good explanation for what's wrong with the volume, because at this point on my side, I think I did everything I could. So let's go back here. Right. So I want to talk about the top problem. What does a graph mean? A graph means I draw a network. Here's a network. And there's a reason why I drew the circles to be circles. It's because now I'm going to go and try to color this. I'm going to try to color the circles so that I'm only going to use 3 colors. And my goal is to make it so that between, for any one of these lines, I don't have both of the endpoints in the same color. So let's try. How do we color these things? I don't know. Let's try to do this. Okay, that was green. I guess this guy is going to be red because I feel like it. And I've got 3 colors, green, red, and yellow. Okay, so I'll color this one yellow. I'll color this one green. I'll color this one red. I guess I'll color this one yellow. Oh, what should I color this? I'm supposed to color it so that I don't have 2 same colors on the same endpoints of an edge. That looks bad because I can't use green, I can't use red, and I can't use yellow. No matter what, I'm dead. Oh, I'll just use yellow for fun. But what I'm going to say is, that was bad. Does this make sense? So this question is asking, can you color the vertices using 3 colors so that no edge is monochromatic? Yeah, okay. Exoplanet, you said you did that on purpose. You're so sharp. Actually, I did do that on purpose. And the reason I did that on purpose is so I could show you what was bad. So I was actually intentionally trying to get it so that I would get stuck. The only way to make it look real on camera is to make it look like you're like, oh man, I got stuck at the end. And I had to actually plan to get stuck. All right. But now what you're saying is we got to fix this, okay? So that's bad, that's bad. How do you fix this? Bad, bad, bad. Let's go and change that color. Can we do that? That doesn't work either. What? Oh, wow. Did I draw one that's not 2 colorable? Well, let's do this. Not 3 colorable. Let's do this. I'll fix that one. Now let's clear out this one. Let's make it pink. I see what I can do. Unpink that one. Make it green. Hey, look at that. It actually works. So if I have this picture, this is legitimately colored using 3 colors so that no edge is monochromatic. See, I've done it. So actually, the way I should say this is, it's not can it be. Actually, I want to change this example also. It's not can its vertices be colored using 3 colors. I want to change this one to find a 3 coloring, right? So just find a 3 coloring. Let's suppose actually that there is something that's already 3 colorable, and I want to find one of these 3 colorings. Okay? How to change? You're asking how to go and change the color. I was just changing the color by undoing some decision and then redoing it with a different color. Because when I look at this, now I happen to have that there's no same colors connected by a line. But now when I look at this picture, you see it's efficiently checkable. The notion here of NP is that if I draw you this picture, you can look at it, and it's not going to take you don't have to try all of the different colorings. You saw as I was trying to fix it, I was like uncolor, recolor, uncolor, recolor. And as you keep making all those decisions, it can take you too much time. Not too much time, it can be very, very time consuming, and it might actually take a really long time. But the point of NP is, if I had just come and first done that right away, you guys would have said, hey, it works. We have found a way to color it with 3 colors. So what I've just shown is that if somebody gives you something which is colorable with 3 colors, then if you were lucky, you could actually come up with that coloring and check it really fast. And that's what NP means. Non-deterministically, meaning got lucky. P means polynomially time checkable. I hope this was somewhat understandable or interesting. The way to think of it is just think of my example of New York City walking around trying to find your shoes. It's like you found the shoes. When you find the shoes, you know they're yours because they smell just like yours. Well, hopefully that's not how you decide which your shoes actually are. But you look at them and you can quickly and efficiently verify, those are mine. It's just that in order to find them, it may have been that you went hunting for a very long time. Temp ID asks a deep question. How did you lose them in the first place? I think that would be the hard question of the day. All right, let's continue on. I have some more questions that people had asked. And I really see people are saying that there's an issue here with the sound volume. So I'm quite curious what that's about. Oh, wow, interesting. I see. So we have a question from Chloe Fua asking what are some of the most important contributions of John Conway? And there's a second question that has nothing to do with John Conway. So I'll start with the John Conway. People often know him as the person who invented what's called the game of life, which is a interesting way of having a bunch of rules of how some cells could replicate or die. And consequently, just with some really simple rules, huge patterns can emerge, even with things flying around. And that's interesting because it shows that from a very simple set of rules, you can get something very complicated that almost looks like it was designed to be special. But I would say if I was to think, how John Conway's mathematics intersected with my consciousness, it would probably be that he actually did a lot of amazing work in thinking about symmetries. Actually, there's something called group theory, but you guys can also think of it just as if you happen to look at a really symmetrical object, you can sort of say, what does symmetry mean? Symmetry means I could just like turn it this way and it looks exactly the same. Or I could turn it that way and it looks exactly the same. Oh, what if I turn it this way and then that way? You can start thinking about all of these different things. And he was able to conceptualize some really, really complex symmetries. And to me, this is amazing. I mean, to me, to be able to visualize really complicated things that happen to be symmetric, which defied the work of many other mathematicians, is remarkable. So this is a very creative person who had amazing ways of seeing things, visualizing things. And another thing that was really great about him is that he spent a lot of time also interacting with less famous people, like myself, like other younger people. He always would go to this program called Canada-USA Math Camp, and he would always spend some time talking to the junior people who are growing up, who maybe want to be mathematicians. And that was actually quite a good contribution as well. But the world has had a loss from him not being here anymore. The next question was, will my different way of solving quadratic equations work for all kinds of quadratics? The answer is yes. And just to save time on this particular live stream, the way I'll say it is that there's a video on this. It's already on our channel, this Daily Challenge with Po-Shen Loh channel, this YouTube channel. It's free. The video is free on this channel. And there's a 1-hour video which talks about like all the different kinds of quadratics that you might come into and how you can solve all of them using that insight with this different way of solving quadratic equations. So that would be my answer I'll give you for this one. And the reason, by the way, why I was excited about this is I was actually trying to come up with another proof of the quadratic formula. That was actually my starting point. And so if you think about it, if you can prove the quadratic formula, you actually can solve all quadratic equations because that's what the quadratic formula does. Okay. What else do we have today? I heard that there were 3 questions. So what else do we have? Whoa. What is this? Let's see. For all real numbers b and c, such that the product of c and 3 is b. Wow, it's so hard for me to read words and understand the math. So I'll write 3 times c equals b. Now I understand that. Find the expression that represents the sum of c and 3 in terms of b. Is this a trick question? I'm not sure I understand this question, because if I just need to know what is c plus 3, I think that Jiang Michael already figured it out. You just take that c equals b divided by 3. And then so I guess this is just b divided by 3 plus 3. So now, whenever I look at this, I'm not sure I'm missing something. It could be that I misunderstand the problem. If anyone else thinks that I've misunderstood the problem, please tell me what to do. But the hardest part was reading the question for this one. Oh, by the way, I saw that James the Normal Guy has said, can we imagine the streets of Los Angeles instead? Yes, you can. So if you want to imagine that for the P versus NP problem, if you're thinking about losing your... What would you lose on the streets of Los Angeles? It wouldn't be shoes. That's New York. In the streets of Los Angeles, you know what you lost? You lost your tires. Although I have a feeling that if you lost your tires on the streets of Los Angeles, you'd probably notice, because your car might not be able to keep moving. Okay, enough of that analogy. But yes, you can imagine the streets of Los Angeles and you lost something. Great. You lost your money. Well said, well said. Kiko Boy says, you lost your money. Well said. Okay, what else do we have? I actually don't know if there's another question after this. Nope, that one looks like the last one. So you know what? I'm going to go back to that one, and I'm going to wonder. Yeah, I don't know what was the meaning of this particular question. So yes, let me instead, so let me do this. So because I happened to get a question that came in about real numbers, let me hit that before we go into general Q&A. Because the way I usually run these sessions is that I spend, a good chunk of time answering some math problem or some world problem using math to everyone. And then we usually save half an hour for random questions. But today is a special, so we're going to go all the way until 9. And that means I have a little bit more time to answer another question. And the other question it's from Baddy Goody Goody Goo, GXTG, asking, what is a real number? Is there a fake number? That's the question. So I guess the question here is, why are we calling them real numbers? Right? What's up with real number? So if you have something called a real number, the real number would be something which I think it would be the opposite of the imaginary number, right? Because we have these imaginary numbers too. But the reason why we call real numbers real is because we actually think of them as corresponding to real things in the real world. In fact, every real number in the real world can show up. Suppose I gave you a real number, and suppose that real number I want to talk about is the real number e to the power 3 plus pi. What is that? I don't know. It's just something. I mean, it's going to be some number. E, by the way, in case you haven't seen E before, we talk about it a lot on the live streams that we run every day. But in case you haven't seen it before, E is this number, 2.7182828459045, and it keeps going. That's E. How about pi? Pi is some other number. 3.1415926, and it goes on. So what is this? If I take e to the power 3 plus pi, oh, I see somebody said they have never heard of e. Well, you'd be welcome to show up on our daily live streams if you want. They're free and they're on this channel every single day, every single weekday. And what e is about, e is something that appears in all different ways in mathematics. And one of them actually that it shows up in is if you were trying to rearrange, so if you had like a whole bunch of people go into a room and everyone took off their hat, pretend that everyone has a hat, pretend all the hats are different, throw them all in the air, and then somehow the hats come back down in some random way and everyone grabs a hat, the probability that everyone got the wrong hat actually is 1 divided by e. So it approaches, it's very, very close to 1 divided by e. So this is where this e is important. But why I went and put this thing here? Why I put this thing here is I said, you see, this is just going to be some number. I don't even know what's that number. That number will be about 2.7 to the power 6-ish. What's that? I don't know, like around 3 to the power 6. Probably it's around 700 something. That's my random guess. I don't even know what it is. Maybe someone here with a calculator knows what it is. My random wild guess would be it's somewhere between 600 and 700. But it's going to be something, right? Some number. But it doesn't matter. That could actually show up if you measured a distance. Like this is actually a number that could show up as a measurement. You could actually say that you have, a person and their house. And that distance between them could actually be e to the power 3 plus pi. If you got really, really lucky, right? So what I'm trying to say is that these are real numbers and they can be used to measure real things. You like the house? Yes. 3 to the power 6 is 729. That's actually why I was making some guess. Now I'm going to revise my guess now. My guess is now around the 500 range at this point. But because 2.7 is too far away from 3. But it doesn't matter. So I'm saying that a real number could measure this. Ooh, 464. That's not far from 500. Okay. Well, now, there are other kinds of real numbers. Real numbers are not all positive. You can also have real numbers which are negative. But that's also something that could be a real thing. You have negative numbers, for example, whenever you have a temperature that's kind of cold. You won't get to negative 464 degrees Celsius because of something called absolute zero. On the other hand, if you want to measure distances, it's very reasonable to say, if you walked backwards by that amount, you've just walked that negative distance. So what I'm saying is that the real numbers can actually measure something that's in the real world. Those imaginary numbers or complex numbers generally don't correspond to measurements of lengths. They're just useful for putting together information in other ways. So I think that's why people would say, the complex numbers will generally not show up as a reading that you could get when you're measuring with some device. On the other hand, the real numbers, you would. Okay, so this takes us to about 8:30. And then what we usually do here, I see people keep saying the volume has an issue. I'm really curious what's going on. I'm going to go and peek at this. What's going on here? Well, it seems like it's actually recording. So this piece is recording. My gut feeling is that YouTube may have changed their algorithm. Oh my goodness. Somebody's watched one of my videos before and said -5 sheep. You clearly paid attention to my videos. Amazing. Yeah, with the volume changing, I'm actually not really sure what's going on. I wonder if there's a difference in YouTube's streaming algorithm nowadays. Okay. Right. So what we're going to do next is we're actually going to go and switch into the second part of the program. And the second part of the program is one where I just go and answer questions that people might have about all different kinds of questions. And usually what we try to go around here is about maybe applications of mathematics or how to learn mathematics or these kinds of things. And you may be wondering why I seem to be looking at the ground and moving around. And the people who have watched this stream before know exactly what just happened, which is that this is how I make it so that maybe I can be a bit more visible. And yes, exactly, I was getting my paper together. And welcome back to the channel for all of you who have been here before. So now let's go and go into this random Q&A, which is another fun part of this session. So what do we have here? What kinds of questions should we answer today? People are still saying too loud, and again, I'm not entirely sure what happened on the volume. I will say I have noticed that the way that YouTube is handling things is that sometimes it takes the image that I send to YouTube, and sometimes that image gets darker, or sometimes it's brighter. And maybe there's something going on which is about the audio, which also adjusts. Yeah, try turning the volume down. Well, that's easy. I can do that. Let's turn the volume down. One reason the volume was high before was because people had asked to have it a bit louder. Okay, let's start answering some questions. Okay, Eleanor Chen has asked, what is the probability of there being a second wave? So I assume you're talking about COVID-19. My opinion is, and I'll just say it's an opinion. I'm not a trained scientist on COVID-19. But my opinion is that the probability of a second wave is extremely high. I would put it as at quite close to 100%. I would probably put it into the high 90%. But that's because I see the world as a mathematician. The reason is because as a mathematician, what we know is that the way that any disease spreads, or any process which causes replication, until you actually have people until you have a lot of people who are already immune or non-susceptible, you're actually going to see an exponential growth. Things are called exponential growth because when there's one infection, that infection typically causes multiple infections. And so it starts to multiply. And the only way that the multiplication slows down is if what you end up seeing is that it's trying to multiply, but it multiplies onto people for whom they've already been immune. And we don't have enough people who are immune yet. So that's why I guess my opinion would be it's quite likely that we'll have a second wave unless we do something about it. And what we should be doing about it is we should be finding ways to reduce the possible spread, reduce that exponential explosion. So what I mean by this is that, when we're saying that each person infects a few people, if that few people can be some number which is less than 1, then that will die out, the infection will die out. And so what we need to do is we need to find ways so that when you have somebody who infects some other people, then the number of those other people who get infected is actually on average less than 1. And some countries actually seem to have been coming up with approaches that seem quite effective. And so we hope that we'll be able to do that here too. More questions. I see that there are some people asking, what did we learn today? Well, I hope that the first segment of this joint session with the UCLA Math Circle today helped people to see what this P versus NP was about. Because the P versus NP is actually one of the most important fundamental questions in both mathematics and theoretical computer science. Okay, more questions. Ah. Okay, so I see Spaced Out has asked how to apply I in real life. Oh, that's interesting. I mean, I actually just did that on some code that we were doing for the Novid app, which is trying to stop the spread of COVID-19. I can tell you what I was trying to do. What I was trying to do is I was trying to have, I had about 100,000 pairs of numbers. So I had 100,000 numbers and another 100,000 numbers. I needed to take the first number squared plus the second number squared with a square root. Okay? Does this sort of make sense? I just was doing 100,000 calculations. That's actually related to sound processing because the heart of the Novid app is analyzing sound waves. So I, for some reason, had 100,000 numbers and 100,000 more numbers. And I needed to imagine that they were like the two legs of a right triangle, calculate the hypotenuse. And I had to do this 100,000 times. So yes, Samuel Ding said you made a for loop. That's what I did the first time. And it was really slow. So if any of you like programming computers, there are different programming languages in the world. I was programming something on the iPhone. The iPhone uses a programming language, it uses Swift. That's what we use. Some people use Objective-C. You can also use C++. But if on the language called Swift in the iPhone, if you write a big for loop that goes through 100,000 things, it is mysteriously slow. Here's how I know. When I saw it was so slow, I just couldn't believe it. I said, what do you mean? This iPhone, this is supposed to be able to do calculations at 1 billion calculations a second. You're telling me that like 1 million of these calculations already took an entire second? That was unacceptable. And so I wrote another for loop just to try. And all that for loop did is it just counted from 1 to 1 million and it added 1. There's no calculation really going on there. And it still took too long. It took like either 100 milliseconds or 1 whole second. Unbelievable. And so what I had to do is I had to find a smarter way. So now if the for loop doesn't work, and I actually need to do this like 100,000 numbers and 100,000 more numbers, and take the sum of the squares and a square root, sum of the squares and a square root, sum of the squares and a square root, what could you do? There's no for loop left, right? Well, here's what you can do. It turns out that, of course, the computer or the smartphone is capable of doing things 1,000 times faster. It just so happens to be that if you use the for loop, the way that it processes the for loop is it's like, yeah, now what do I do? Yeah, now what do I do? And you just keep telling it what to do, and it keeps asking you, yeah, what do I do? As opposed to it just being saying, instead of it just saying, gotcha, I'm going to do that bunch of stuff and I'll come back to you when I'm done. That's the best way to think of this. So I used I. So it turns out that there's something you can do inside the iPhone where you're able to pretend, there's a function you can call, there's something you can do when you're programming the iPhone, where you say, just kidding, this was not 100,000 numbers and 100,000 numbers. Actually, it was just 100,000 complex numbers. So what I actually did to do this program is, remember, I had 100,000 numbers and 100,000 more numbers. And so what I did is I had one command. You tell one command to the iPhone to say, hey, iPhone, just kidding. You can reinterpret these as 100,000 complex numbers, where it's the real part plus I times the complex part. And when you tell the iPhone that, the iPhone says, gotcha, I'll come right back to you after I pack all of this together as 100,000 complex numbers. Because remember what I said. What I said is, as soon as I wrote this program, I said something's wrong. The iPhone processor can go 1,000 times as fast as this. And the fact that it's not going 1,000 times as fast means it's just not interpreting my commands. A for loop is saying, all right, do this now. And then the computer is like, done. Yeah, what's next? And it just keeps going back and forth and back and forth. And all this lag is terrible. So instead, I just told it one command, which is not a for loop. It's a special command. Consider this to be 100,000 complex numbers. One command. Pow! It was done like that. Because remember, it's got 1,000 times speed up when it just has one thing to do. Then the next thing that you do, I told it, you see this thing I gave you with 100,000 complex numbers? I want to tell you all the magnitudes of them. All the magnitudes. What are magnitudes? The magnitude of a complex number. Let me switch back to the blackboard just because I want to maybe mention that. Let's go back to the blackboard, right? When you tell something that I've got a bunch of complex numbers, right? If I've got a bunch of complex numbers, imagine that the numbers that I had originally in this sequence, maybe I had like 3 and I had 4 and I had 1 and I had 2 and I had -1 and I had 7, right? I have all of this stuff. That was what I actually had. And then what I did is with one command, zoop, it became 3 plus 4i. 1 plus 2i. Minus 1 plus 7i. Okay? And then I said, now calculate all of the magnitudes. What's the magnitude of a complex number? You were asking me what's a real-life application of I. I used this to get like a 100 to 1000x speed up on a computer program. The magnitudes are square root of 3 squared plus 4 squared. Square root of 1 squared plus 2 squared. Square root of negative 1 squared plus 7 squared. And so that was it. Actually, by doing this, the program became efficient. And for any of you who have Novid running on your phone, if you happen to have an iPhone that's running Novid and detecting how far away other devices are, every single time you press the scan button to go and find out how far away the nearest device is, it actually does this thing I just told you. Like the actually deployed version of Novid that you can download. The way I overcame that huge delay was by giving these two pieces, making the complex number thing, and then calculating magnitudes. So it's very useful in real life. And if I hadn't done this, actually you'd lose a lot of battery power, because when the CPU is computing like that, it actually uses a lot more battery power, and also detecting distances between devices would have taken longer. And if you're wondering, wait a second, doesn't it take a really long time for the computer to take this, and then take this, and then make that? The answer is actually no. When I snap my fingers, that is an instantaneous operation. Because the way a computer stores information is the computer had a list of 100,000 things, and the computer just knows the list starts here. It's basically that there's some stuff in memory. There's a big block of memory with 100,000 things in a row, and the computer knows, or the smartphone knows, it all starts there. And then the smartphone knows the other one starts there. So when I did this packing thing to make them into complex numbers, all the computer did is it said, hey, there's going to be these things, and they start there and there. The real part is there, the imaginary part is there. So yes, these are called pointers. So some of you here know something about computers, and so hopefully you got a kick out of this. But for anyone who is wondering, is I ever useful? Oh yes, this thing made Novid more possible. Okay, more questions. Let's see. Oh, Joshua Wu, you're asking about school. Which APs do you recommend taking in high school? Oh my goodness, there's a lot of APs. I understand that there's even like AP Environmental Science, and there's like AP this and AP that. And some people even talk about there's like some AP exams which you don't even have to take the class, but if you just, got a book and studied them, then you'd be fine. Yue Cai Chu asked, what's an AP? An AP is an advanced placement exam. It's just something that a lot of people in high school take. These are like classes that are harder. They're harder than the usual class. And somehow it looks good if you're applying to a university and you took some AP exams, because then somehow people think that you challenged yourself, right? So these are usually harder classes than the usual ones. Some people take a whole ton of AP classes to look like they are, smart people. My attitude is that somehow I don't think that it's really worthwhile to take too many AP classes. I don't think that you actually gain too much by trying to just show you have taken more APs than other people. I think if you want to show that you have done great things, it's much better to actually do some harder things as opposed to just more things that you get scores of 5 in. 5 is the maximum score for the AP. Oh, Spaced Out asked, well, is AP Calc worth it? Of course, because when you're doing mathematics in school, you will probably study calculus at some point and might as well take the AP Calculus. You have to take math, so you might as well take the AP version of math. But what I'm saying is, don't just go and take like random AP exams because it seems like you want to have that prize called took the most AP exams. I don't think that's important. So instead, I would say, take the APs for math, the APs for science, like the biology, chemistry, physics, that kind of science. Those are legit. Those are really, really interesting. You will gain a lot by taking those. But then there are a lot of other APs that I would say only take it if you actually are interested in that. Okay, more questions. Oh, interesting. Somebody said, how close can you actually get to a non-terminating decimal distance? So, I said the real number could be a distance. And in that sense, I think I may have been lying, in the sense that there are actually, you actually probably can't get every real number as a distance. What do I mean by this? What I mean by this is that, I'll tell you, okay? So, what's a distance anyway? A distance is like something I could describe. And I'll tell you a distance. From me here to the front right tire of the car that just beeped out on the street. That's a distance, right? Here's another distance. From me here to the classroom in mathematical sciences building where the UCLA math circle is usually held. That's a distance too. But all of these distances I can express to you as sentences. So I can tell you a sentence, and that sentence describes the distance. That seems to make sense, right? Of course. Every distance in the world, you should be able to say a sentence that describes it. Like here's another distance. From Earth to the moon. That's a distance. Well, here's the problem. If you count how many different sentences can be written, the number of different sentences which have finite length. You could have like really long sentences, but if I'm saying the number of finite length sentences, that number is actually what's called a countable. It's countably infinite. And so it actually turns out that there are more real numbers in the world than there are sentences to describe them. It's actually true. So somehow, so what I just said about real numbers, maybe that's not quite true. It's like in theory, it could maybe represent a distance. But unfortunately, there are actually more numbers in the world than there are sentences to describe them. And that's a really nifty fact. So, okay, that was a good question you asked, by the way, because it also shows that I was not quite right in the answer I gave you. More questions. And of course, if people are asking what a real number really is, there are some formal definitions that you will learn in college in math class of how you can construct these real numbers, given that there are so many of them. Kiko Boy asked, what's the best way to learn math? By doing something yourself, which is somewhat similar to what you have just seen me doing here with the questions that are coming, which is to think about whatever you're facing and try to own it for yourself. You're not doing math. You shouldn't do math just to give an answer to somebody else. You should do math problems also to satisfy your curiosity, even if someone else assigned you the problem. Like today, you guys assigned me all kinds of problems to think about. And each one of them, I'll just let it kind of tickle my curiosity and ask, hey, what more can I see in this? Like, is there something else here? Is there something deeper? Why is it this way? And the more you think about math, the easier math will be. And I think that a common theme of many professional mathematicians is that they weren't necessarily people who just did tons of contests and won all the contests. You can do that, of course that's great, but that alone doesn't make you a mathematician. What makes a mathematician unique is that we're just really curious about, why is this? Like, how does this structure fit together? John Conway, he thought about those things all the time. He wanted to know about these high-dimensional structures. And so if you just go and think deeply about whatever you're learning, that's the best way, in my opinion, to learn math. It is not just to do a whole ton of practice problems that are all the same. And so, for example, whenever I'm teaching math, the way that I usually teach is I intentionally will give problems that you don't know how to do. That's by design. I don't think you should already know I don't think you should already know how to do the problems. If you already know how to do them and practice them, and that's just practice, then that's not so interesting. But it's much better to go and give you problems for which you shouldn't know what to do to start, because then you get to fight with them and then learn how to do it yourself. Okay. More questions. I see that some people here have some broken calculator questions. Come to the live stream on the weekdays and you can see. Shanti Lu asked, what was your dream job as a child? Now, I think for me, I was, of course, influenced by my parents, and it just so happened that my father was a statistics professor. So I was able to see what the lifestyle is like being a college professor, a university professor, and it seemed really interesting because it seemed like he was always messing around on a computer doing something. It was called research, whatever research is. It seemed like he was always trying to figure some new stuff out. That seemed kind of neat. And then at the same time, I would see that he also was the kind of guy who liked talking. He liked teaching. And so when we were at the dinner table, we'd often hear him talking about how, when you teach a class, it's like being a stand-up comedian. He'd say these kinds of things. And I thought that was kind of fun. So I was always thinking, it would be fun for me to do this. Except that, I didn't go into be a statistics professor. I love math. I love teaching math. So I ended up wanting to be a math professor. I guess that's what I am now. But at the same time, I think some of you who are the people who follow me, who see the sort of stuff that I usually do and who come to my live streams, you know that I'm also not the typical math professor. So I think my dream job was always a hybrid of, yes, one part math professor, the other part someone who gets to do some funny stuff that has maybe some real world impact, preferably involving lots of computers. And that's what I always wanted to do. I guess that's what I'm doing right now. So I guess that also goes to show, maybe if you have something in your mind and you just keep moving towards it for like 30 years, after a while you kind of steer in the right direction. Okay, more questions. Oh, I see so many people are asking about this log base e. Why is it a natural logarithm? I'll tell you why. It's because log base 10 is not. What kind of a ridiculous number is 10? Does anyone know what is the significance of 10? You know the number on your calculator, the log base, the log is log base 10. What kind of crazy person chose 10? Why is 10 so important? It's because the crazy person was a person with 10 fingers. The only reason why we use 10 at all in this world is because we have 10 fingers. There is no fundamental reason why you should use 10. In fact, computers don't use 10. Computers use 2. And in fact, that's much better. You shouldn't bother with this 10 nonsense. It's just that human beings happened to be able to count on their fingers. And human beings wanted to have these fancy ways of saying, you know how you multiply a number by 9? If you want to know what's 4 times 9, you take your 4th finger and you just put down the 4th finger. And look, it's 36. Okay. Well, anyway, that's like why we use base 10. That's why 10 is so important. And it's not. Actually, 10 is completely not important. And so actually the log base 10 is the unnatural log. Now you might ask, what about e? Why do you care about e? It's actually because if you take the log base e, then it has some nice properties. If I take log base e of 1.002, do you know what it is? Actually, any of you who have access to Wolfram Alpha, try this. If you or if you're on the computer, type ln parentheses. Don't do 1.002. Do 1.000314. Okay, just do that. And just type that into your calculator. ln of 1.000314. I forgot how many O's I said. But let's do 3 O's and a 314. Okay? ln of 1.000314. What do you get? Oh, look at that. 0.000314. If you round it. How many people think that's neat? ln of 1.000314. It's just like, forget about the 1. Forget about the first one. It's just 0.000314. Hey, it works for other things too. You know what is ln of ln of 1.000576? Maybe even if you don't have a calculator, you might have a guess. ln of 1.000576. Hey, it's 0.000576. Do they have to be less than e is the question. Well, try this one. What about ln of 0.999333? That would be easy. 0.999333. And see if you guys can figure out the pattern. So I want ln of 0.999333. That's still less than e. You're right. But let's see what this is. And let's see if people can guess what the pattern I'm going for is. ln of 0.999333. Now it's not 0.000333. It's negative 0.000667-ish. Does anyone have a guess of what happens if I take ln of 1 plus a really tiny number? And that tiny number, I mean close to 0. If I take ln of 1 plus a teeny thing, the answer is about just that teeny thing. I don't want to say the answer is 0. I want to say ln of 1 plus x is very close to x. That's what Joshua Wu just wrote. It should be very close to x. ln of 1 plus x is very close to x. Hey, now those of you who like log, that log is the log base 10, try doing the same thing. Try doing log of 1.000314. It won't be that nice. If you do log of 1.000314, Then, while people are typing that in, Evie Shen asked, aren't we really overtime? Well, when we do a collaboration with a math circle, we run for 1 hour. So we are still under time by 5 minutes. But if you did the LOG, 0.000314, the LOG in base 10, it's not 0.000316. It's actually going to have some, it's not going to be as nice. It's going to actually be some smaller thing. I don't know if anyone here is actually typing that in, but we actually want the LOG. Yeah, there you go, 0.000136. Not as nice. LOG of 1 plus x is not just x. Those of you who know log rules can probably tell, like you can explain how much, like what the factor is. But what I'm trying to say is, hey, that's why ln is really nice. ln of 1 plus x is about x. That's neat. That's very natural. So hopefully that helps to explain why this is a natural base. All right, what kind of questions here? Yue Cai Zhu. What is the difference between ln and log? So the log is basically trying to answer the following question. Log of 1,000 is 3. Log is in base 10. So log of 1,000 is 3 because 10 to the power 3 is 1,000. So all that log is trying to say is 10 to the power what is this? ln is just asking e to the power what is this, where e is 2.71 whatever. That's the only difference. All right, more questions here. Let's see what we've got. Actually, usually on these weekend ones, we don't do as many math questions because the weekday show is where we do lots of math questions. So I'm going to try to see if there's something more general here that we can hit. Lawrence Sun has asked, why don't you monetize your channel? Well, this one is what we made a decision early on. This channel is just something that we're going to do for fun. And our decision of whether we do more of it is not based on the monetization. It's based on whether more people come. And that's why we love working with people like the LA Math Circle. Let's go and see. What else do we have here? I'm always looking to see if we can end on some, more general types of questions. Yes, Zhao Yan Zhang asks, how would you prepare for math competitions? As those of you who know on this live stream, the number one advice is to make sure you eat a banana. That's a not serious advice. But actually, how you prepare for these math competitions, go and challenge yourself. You know what is hard, you know what is easy. If you see something that's too easy, don't waste your time on it as you're preparing. You really want to make sure that you use all of your time to go and push yourself. And it's the same as what you do in sports. You need to be able to have a feeling in your own heart, in your own, well, not your heart, feeling in your mind, of when am I doing something that's actually stretching me, and when am I doing busy work. If you find yourself doing busy work, quick, get the busy work done, or preferably find a way to not be assigned busy work, and then go and focus your energy on something which stretches you. And it's a great feeling. It's just like in sports. I don't know if any of you play sports, but like somehow the feeling of actually having gone all the way to the limit is a nice one. And you just feel like you're a stronger person afterwards. So do the same thing with your mind, with math. What sports do you enjoy to play? Asks Harry Liu. Actually, the sport that I really enjoyed was ping pong. I loved playing ping pong. Maybe because I liked to try to stretch myself to see if it was possible to whack every ball as hard as possible. I just thought that would be fun. And so yes, it was a challenge. And it was a fun challenge to do for many years. What other questions do we have here? So Eleanor Chen has asked, will you continue with daily live sessions in the summer? Possible. Our decision is all based on watching the number down here. And so if this number tends to be quite large and or growing, then we decide that we'll keep doing it. But as you all know, I'm balancing my time with, for example, trying to stop the spread of COVID. And so we have to make our decisions based on that. Okay. I see that some people are asking, when will I wear a green shirt? My understanding is that on our forums, there is apparently some sort of an upvoting competition. And somehow I believe I've already agreed that I will wear a green shirt at a certain point. But really, realistically speaking, that might be one way. Another way would be if we actually break through on all the things we're trying to do. Okay. What other questions can we do? There are somehow some general questions that we can use to finish off for today. Yes, Cool Kid has asked, how did math influence your life? I'll use this one to finish up. So I would say that math influenced my life by helping me to become more strategic. There's something that many people say, which is that hard work is the answer to everything. You know, have a good hard-working attitude. That's important. Actually, I see too many people who are smart and lazy, and that's just useless. Hard work is very important. But unfortunately, if you have a really hard work and good work ethic, and you try to do it on the wrong strategy, you also don't get anywhere. So what math has always helped me to do is that with math, you look at the world and you quickly find out what is the main reason for the problem. You know, like you can even use some quantitative measurements, your estimates. You can be like, oh, you know, this thing is close enough to 200. That's close enough to 1,000. You know, maybe I'm supposed to multiply those two things. That's 200,000. And after a while, you figure out, oh, yeah, you know, we've got this big problem to solve called the spreading of COVID-19. What's the real problem? Oh, there's a real problem. The real problem is that people are spreading half of it. Half of the spreading is happening before you're contagious. And each person typically spreads to like about 2 or 3 people. So you immediately find out that, oh, unless you stop the spreading before symptoms show up, you've lost the game. Right, so that's actually how I ultimately then decided to dedicate a few months of my life just to try to solve that one problem. And so math has changed my life in fundamental ways because whenever I'm looking at anything complicated, I go and think, what is the right way for us to intervene? And then, can we use math to make some really inefficient things more efficient? Like using the I today, the thing I showed you about the I, to find the square root of the sum of the squares of 2 numbers really quickly. All right. Well, that finishes this weekend show. I don't have a show tomorrow on this channel, but we'll be back every week, actually, on Saturday at 8 o'clock p.m. to usually it's 8:45 when we're just doing a general show ourselves. It's until 9 o'clock when we collaborate. And if you enjoyed this and you want to ask more serious math questions, that's what we do during the week, 4 o'clock to 5 o'clock Eastern time every day on this channel as well. People just ask random questions. And on that one, I actually try to mainly answer the math questions, I don't answer as many questions about bananas. And for those of you from the UCLA Math Circle, thank you very much for coming. Professor Radko, if you're here, if you're listening, I want to say thank you very much for organizing this collaboration. I actually still remember volunteering to help give a lecture at the Math Circle that you organized way back when I was a PhD student of Benny Sudakov, also living at UCLA. So somehow UCLA does hold a special spot in my heart. Well, thank you to everybody, and I'll see you all next time.